Hello, this is Dr. Mary Nawal Sabrajmaye. In this chapter on PLCs, we are going to talk about the process control and SCADA systems. In this chapter, we are going to discuss types of processes, control configurations, closed-loop control, PID control, and SCADA systems. To begin with, we are going to talk about the different types of processes. The continuous process is a process that runs continuously. It has raw material entering from one side and finished products getting out on the other side. In this example, we have engine blocks coming in here. We have different parts in the manufacturing, namely automated machine assembly, hand assembly, then adjustments and checking. And on the other hand, we have the complete engines exiting on this side. In a batch process, on the other hand, we don't have any flow of product material. We have raw material entering a batch, our processes inside the batch. For example, in here we have 3 different types of material from 3 different inputs. They are monitored, they enter the batch. We have in here a mixer motor. We could have several other parameters, and then they are going to exit after a certain time from the batch. In discrete manufacturing, this is an individual unit production. For example, in this image, we have a robot manufacturing an object. This process could take minutes to hours, but it is a one-by-one individual process, so it is a different objective from the other two. So any of these has a part in different control configurations. So in control configurations, we are going to talk how the different machines are being controlled. Individual control is one PLC controls one machine. So this is the simplest form. I don't have any communication between the different machines or the different PLCs. The PLC could have a screen, it could have an HMI, but they are all connected to the one same machine that they are controlling. In a centralized control, I have one main controller, usually a large PLC with several units, that is controlling the whole process, so it's controlling several machines and several steps that have to be synchronized together. The advantage is that since the control is made from one same controller, the synchronization is more evident than if it is made with different PLCs. But on the other hand, if the main controller fails, the whole process stops altogether. We have distributed control system. It's a system with 2 or more PLCs, and each PLC is controlling a part of the process, so that if one of the PLCs fails, doesn't make the whole process stop. So in here we have a host computer controlling the whole process. It could have one centralized human-machine interface, and we have several advantages to this. As we said, we have a PLC controlling each part, so if one of these PLCs fail, doesn't make the others stop working. It also has smaller cable lengths because the PLC is close to the machine it is controlling, so the cables between input, output, and the motors and sensors are really short with respect to the other system, where if I have a centralized PLC, the cables are going to be tall between the PLC and the different motors. On the other hand, it is a system that is more complex to construct because it has to have communication. It has a communication protocol that has to be downloaded on the computer to be able to control it. And so we have cables in here. We have a system on the host computer. The host computer can monitor the outputs of the different PLCs, can also control the different PLC functions. Closed loop control. Actually, all analog control is made usually as a closed loop because we are going to read from a sensor the actual value and we're going to feed it back. We have a required value, a set point. This set point could be a value that is a constant from within the program, It could also be a parameter that we can enter on screen or on the table, control table. And then we have the error signal, which is the difference between these two values that is itself the input to the controller. And then I have the machine, and then I have the sensor again that is going to read the new value of the signal to check if it is equal to the required value or not. So this control, the feedback control, is the simplest form of a PID control because it is the proportional control. The proportional control creates an output that's just proportional to the error. So it is a K times the error itself. The integral and the derivative are going to help this control to stabilize, and we're going to see it. So the integral responds to the size and the time duration of the error. So it's going to take time into consideration because it is the integral of the value that has been outputted here. The derivative is the derivative, mathematical derivative of the error. So it is related to the slope of the error, that is the variation speed of the error. So in here we have an example of a proportional control. You can see that a proportional control doesn't stabilize very quickly. It overshoots, then it tries to stabilize. If I want the overshooting to be smaller, I have to have a control that is much slower, and this means that the production rate is going to be very low. If I want to increase the speed, the risk is that the controller may become unstable and oscillate infinitely and never reach the set point. Another problem is that usually when I have a proportional gain only, I have an offset error. So whenever it reaches the set point, whenever it stabilizes, it still doesn't stabilize to the exact value. The integral gain, which is also called reset time, acts as a stabilizer. It stabilizes the signal and corrects this offset error. The derivative gain, which is also called the rate, is used to slow down the controller when the change is too fast. So the integral and the derivative together help the controller to start quickly, reach the set point in a faster way and without overshooting. So to reach these values of a integral, derivative, and proportional, which are the exact correct ones to do a fastest and more stable control, has to be tuned. We have to choose correct values for P, for I, and for D. The simplest way is to go for manual. This means by trial and error, and then the operator checks for the best values and then decides on them. And this is the longest way. We also have semi-automatic, or what we call the auto-tune, is that we study the function of the machine, we calculate the parameters based on the measurements and on the error itself, and we derive the values for the optimal P, I, and D for this machine. We also have advanced control. It is what we call a fully automatic based on fuzzy logic. So this uses fuzzy logic from artificial intelligence methods to readjust the P, I, and D parameters continually as the machine requires. So it can relearn the values every time the parameters change, and this is the optimal one. Of course, it is the most complicated to create. Arriving to the SCADA, which is the supervisory control and data acquisition. Data collection is simplified by using SCADA systems. So this is a way to exchange data between the plant floor. This means all the different PLCs on all the different machines to one supervisory computer. And this allows data logging, data display, and the study of the trends of the data that is flowing all through the system. So in a typical SCADA system, independent PLCs perform input-output control functions on their own machine, and then they are only being supervised by a SCADA or HMI software package downloaded on the host computer. Unlike distributed control systems, SCADA systems usually are referred to as a system that coordinates but does not control processes in real time, whereas the distributed control system has a job to control the other PLCs. This is where we have a difference between SCADA and DCS systems. With this, we reach the end of this chapter. Thank you for your attention.